Am I audible? Guys, am I audible? Are you able to hear me, see me? Everything is good from your end?
Yes, sir.
Yeah, yeah. All right, let's start then without any further ado. So can someone just take the onus of summarizing what we did yesterday? Yeah. Can someone do that? Karan, can you do that?
Yes, sir. Sir, first we discuss about how the earlier data structures were inefficient. Their time complexity was less. So we first discussed about arrays, then about linked lists, then we saw about that DAT that we saw that, and then it was consuming lot of space. So then we introduced hash tables. I think that's it. Then we need to choose a well-behaved function so that that space is less, time complexity is less. Then you also introduce the topic of open addressing. In that, how we put elements, if that like function, if function f of x we have chosen like x modulo 10, then if there is 77, we check that if seventh position at the index 7 there is an element. If there is element, we go up, or according to our wish, like which probing method are we using. So
Yeah.
that's
Yeah, so basically, Karan is right. We were basically talking about the need to search in a search space. We wanted to have data structures wherein we can search efficiently on the data, but as well as we wanted to support the ability to insert and delete dynamically. And that's where we were talking about search structures which could help us do that. And we talked about hash tables in particular for that, and we said that hash tables give us on average O1 time complexity for these operations, for insert, delete, inserting any random element, deleting any random element, and searching any random element in the hash table. And so we looked at, so any application of hash table will basically, the underlying pattern in the question will be that you will be actually I mean the question will reduce to you searching something in the data, and as well as inserting and deleting dynamically. So we looked at the question of grouping anagrams together, right? And there we said that the actual search problem is that at any moment of time we need to search from within the existing groups, right? We have some groups which have already been created, and we want to search from within the existing groups whether this particular string, the current string that we are getting, whether it will fall in one of those groups, or do we need to create another group for it. And so that is the dynamic nature of searching in this kind of a question. We had to search for a group from a set of groups, right? And we basically searched it, and if found, we appended this string to that. Otherwise we created a new group for this string, right? So any kind of application, all I'm trying to drive home, the point that I'm trying to drive home is that any kind of application of hash table will have an underlying searching criteria that needs to be met. So what I mean by that is that you have to have the ability to search. The question will be such that it will require you to search explicitly in some search space, as well as insert, delete, right? So today we will be basically covering more and more applications of such hash tables, and we will look at different types of properties that that exist within questions which enable us to use hash tables, right? So does anyone have any questions from yesterday? Like, do you understand the USP of hash tables, what they give us, what is the power that they have, that they empower us with, that enables us to solve questions which otherwise cannot be solved with ordinary data structures? No one has any questions?
So yesterday you told to discuss about the time complexities of queue and stack in terms of the search.
Yes. So what do you think?
So in case of stack, so like during the insertion operation, if we are going to search any random element, it has to be O of n, because we will, if it is one stack, because first we'll have to, sir?
Yeah, it is one stack only.
So first we have to do the searching, and then accordingly, if we don't find the element, then we'll pop it accordingly. So once we find the element, then we'll sorry, just a minute. Yeah. Okay. So if you have to insert like on the topmost position, it will be O of 1, and insertion like if we need to insert a number in between, then we have to pop all the other elements, and then we have to insert that,
which is the sorted stack. If you are keeping an unsorted stack, then it is O of 1, right?
yeah,
If it is a sorted stack, then you might have to pop elements.
pop elements.
Okay.
So in case of deletion, then
And then
if
push them back, right? After you pop them, you insert this element and then you push the other elements back.
yeah, yes sir.
Yeah. Okay.
And in case of deletion, if we delete any top position, then in an unsorted array, then it has to be O of 1. And in case of if we need to delete any random element in case of a sorted array, it also has to be O of n plus n, because we'll have to push back the remaining other elements.
Yeah.
And then in case of searching, like in case of unsorted, okay, in case of the unsorted, then it has to be O of n. And
So deletion is also order n and searching is also order n, right? In sorted also deletion will be order n and searching will be order n. I mean,
yeah.
Yeah. Yeah, others understand this? Right, so we did this, I gave this exercise to, yeah, others, everyone else understands this. I gave this exercise to brainstorm the time complexities for dynamic insertion, deletion, and searching in case of stacks and queues, if you want to use these search structures. And this is the time complexity for each of them. So if there are any questions, let me know. Otherwise, we will move on to applications. All right, let's begin with applications then. So let's try. Let's try this question. So this is, I'll just tell you the number also. This is 166 of LeetCode, question number 166. So any ideas how to go about doing this? So this is a simple question, right? Why is this taking time? So basically in the question, what is given is that you have a fraction and you have to convert it into decimals. And what can happen is the decimal can recur. Everyone knows recurring decimals, right? Like 10 by 3 is basically 3.33333. So it is recurring. So in case of recurring decimals, you should enclose that part in brackets. So for 10 by 3, this should be the answer. For let's say 20 by 7, it should be 2.85 and then 7, 1, 4, 2. And then again you will get a 7. I think it should be this, right? So how do you do this? So what is the underlying structure here? You can divide a number to get the quotient, right? So first thing, see, let's examine any decimal that can occur. Let's examine 20 by 3 only. So 20 by 3 is 6.666, right? So let's examine this. Every such recurring decimal has 3 parts, right? It actually has 4 parts. You have the sign, which is here plus. It can be negative numbers, so that's why we are taking into account that. So the first part is that it has a sign, right? Then this is the second part, which is the quotient. When you divide the denominator by the numerator, what the quotient that you get is basically this. Then there is a decimal or a dot, correct? Now this part, then comes the part after decimal. So part after decimal basically has 2 parts, right? It has a non-recurring part and a recurring part, correct? So in this case, there is no non-recurring part. This is empty in this question, in this example, and here 6 is the recurring part. Sign is plus here, quotient is 6, decimal is dot, and so this is how you dissect 20 by 3. Correct? Similarly, you can take other examples. Some maybe take one from the question itself. Let's take 22 by 7. Let's take, which is pi, right? So pi is 3.1. Then you will have 40, 7, 4, 20, 30, right? 7, 4, 28, and then 20 again. So 2, 14, and then 60, 8, 5 after that. Tell me the entire thing.
5, 7.
After that?
Sir, 1 again, I think.
It will be again 1, right? So this entire part will reoccur again. Correct? So this also, if you talk about parts. This is positive,
But I
this is
think
plus.
pi doesn't recur.
Come again.
As far as I remember, pi doesn't recur anywhere.
Pi
I mean,
doesn't recur.
Yeah.
Whatever, just do the math. Okay, that's not the point. The point is that every decimal can be represented as this, correct? According to the question. So we have to basically find each of these. That's it. That's the question. So sign you can find easily, right? If both of them are, if the numerator and the denominator are of opposite signs, then you can put a sign of negative here. Otherwise, you can put a sign of positive, right? So sign is cool, not a big problem in that. Quotient is fine, right? Quotient, you can simply divide the numerator by the denominator, and whatever quotient you get is the quotient. So you can take the absolute values. Once you have considered the sign, you can just take in the absolute values and do all the operations for all the remaining parts of the decimal. So quotient is fine. You can just divide the numerator by the denominator, you'll get the quotient, right? Dot is dot. You can put a dot after that. Now the main parts, basically. Now the non-recurring part and the recurring part, right? So now how do you go about computing these two? That's basically the crux of the question. So how do you go about doing this? This is simply old school arithmetic, right? There is no rocket science here.
so we'll just take the remainder and divide with the
Yeah, you take the
denominator
and multiply it by 10.
and divide it with again
Divided by
denominator.
the quotient. So you can keep, basically, you can keep multiplying it by 10 as long as the numerator is less than, as long as the remainder is less than 3, the denominator, right? And you can keep appending zeros here, right? That will be the first part, because everyone understands this first part when you append zeros here after the decimal. Others? So first time, basically whatever remainder you get, you will multiply it by 10. There nothing. After that, you will keep appending zeros until you get, and you will keep multiplying it by 10, the remainder, until you get a number which is greater than the denominator. Right? Others, do you understand this? This is simple division, right? There is no. And once you get a numerator greater than this, then what you do is you can simply divide and get the quotient, and you can put in the quotient. And then with the remainder, you can repeat the process. Whatever process you've been doing here, you can just repeat the process. Correct? Will you repeat the process for the zeros also? No, right? Everyone knows this, right? You will not repeat the process for zeros. You will, whatever remainder you will get, you can keep multiplying it by 10 until it becomes greater. Yeah, I can explain it by example, but I think this is not such a big problem to explain by example, right? Let's take a I'm just trying to tell you like how we are approaching the question. Example is fine, I can explain. Like solution is fine, you will understand the solution. So let's take 10 by 11. Okay. So you will have so first part is the sign. So sign, both numerator and denominator are of the same sign, then you can put a plus here. So you can choose not to put anything. If they are of opposite signs, then you can append a 0 here, minus here. Then you have the quotient. So when you divide 11 by 10, you will have a 0. So that will be the quotient. And after that, what is the remainder? The remainder is 10, right? And you have to divide it by 11. So first time what you will do is you will simply multiply 10 to it. That comes at the cost of putting this decimal, right? And after that, you can divide 100 by 11, which will give you 99. So you can take the quotient and you can put it. And what's the remainder then? The remainder is 1 now. Correct? And now basically you have to divide 1 by 11. So you can multiply it by 10 again. So it becomes 10 by 11. Now the next time you multiply it by 10, will you put a 0 here?
Yes.
Yeah.
Yes, sir.
Yes, sir.
So only the first time you will not put, right? Everyone knows this, right? So then you will put a 0 here and then you will multiply it by 10 again. And now you have 111 again. So you can again divide it, put a 9. And then again you are left with 1. You can do a similar process, multiply it by 10, that's fine. And after that you get another 0. So you put a 0 here, 9 and so on. So basically this part is recurring. So the point is, when you are calculating the part after the decimal, there will be some portion which is non-recurring, which is fine. Now the major challenge is the recurring part, right? How do you break for recurring? Or how do you know that now it has started repeating? So when does it start repeating? When you get a digit, when you get a number which you have already like gotten before, then it starts recurring, right? So when you divide it, when you get a remainder which is which has occurred in the past, then you know that after that the process will remain the same. Because the process is the same, it will start enumerating the same thing again. Like here you got a 9 and you know that you had gotten a 9 before also. So now after this, whatever will come will be the same, because you have gotten a 9 and the denominator is always fixed. The part with which you are dividing is fixed. So, and the quotient is fixed. Then basically the entire sequence of outcomes will be the same from here on. Right? Everyone understands this? Do you understand this? Yeah. So basically then what you have to do, you have to check whether you saw this number previously or not. So now let's talk about the pattern. We have done enough post-mortem of this question. Let's now think about the pattern. What is the pattern? What is the question asking you? The question is asking you to search for the existence of an element previously. Right? I can abstract this question to this pattern. Eventually it boils down to this, that I should search whether this element occurred previously or not. And if it occurred, then I can break. So I have to search for the existence of an element previously. And this is a pattern. If you see questions wherein you have to do this, then the first thing that should come into your mind is a dynamic search structure, like a hash table. So basically in the hash table, you store which numbers you have already gotten in the past. And at any point in time, you can search whether this element is in the table or not. So if it is in the table, what does that mean? That means that you encountered this element previously, right? So
Sir,
you can stop.
Sir, still have a doubt. There is a chance that it may have repeat, but not the whole sequence has been repeating. Only a single digit is been repeating. Let's suppose we can take the example of pi. It's 3.145, and maybe there's a chance that one is been repeating, but it's not recurrence, right?
No,
Only by looking at one
if a
digit,
number is repeating, I'm not talking about a digit or anything. Whatever remainder I get, if that remainder has occurred in the past, then definitely the sequence will be the same.
Yes, I got it.
Right? I'm not talking about a digit. It can be a 2-digit number, 3-digit number, the remainder.
Yes, I got it.
Yeah, it is because just think about it, right? Whatever, see, you had a number X, you have a divisor, right? You call it a divisor. So this is called a dividend, right? So you have a divisor, which is the same for throughout. This is fixed.
Yes, sir.
Now you get a remainder. Every time you divide that number by a divisor, you get a remainder, and now you get a new number. Correct?
Yes,
so
sir.
if there are 2 points, when you get the same remainder, what does that mean? How can you write that number? So let's say this number was X. You can write this X as divisor was D, let's say. So D into Q plus R. And let's say the next time you got the same R, what will be the pattern? This R will be the same, correct? And you are dividing by the same number. So what happens next? Next time you take this remainder as the next number, right? So here also you took the same number as the remainder and your divisor is still the same. So whatever will happen now will be the same in this case also, because this is now your dividend and the divisor are same, right? Here
Yes,
your
sir.
divisor was this and your dividend is basically R or R into 10 or R into 100, whatever. Like you keep multiplying it by 10 till you get a number, get an R prime, which is greater equals D. Once you get that, then basically that R prime and that D is your dividend and divisor. Here also you will get the same R prime and D. So the sequence of outcomes after this point will be the same for both the cases because your dividend and divisor are the same. So that's the point. That's the part that we are looking at. We are not looking at a specific digit, right? This point is clear to everyone? Yeah. So just look at the underlying pattern now. That's more important. This math is fine. You will be able to figure out. The underlying pattern is that I need to, at any point in time, I need to search whether the current element that I have, whether the current remainder that I have, whether did I encounter it previously or not. And that is the pattern, which is the golden pattern, which dictates that you should use a dynamic search structure like a hash table. Dynamic search structure, as in dynamic, is because it is a dynamic data structure. It's not a static. You can allow for dynamic insertion and deletion. And search structure is basically because it enables you to search efficiently, search an element. So immediately it should come into your mind that I can use a hash table wherein I can keep storing the elements as and when I get them, so that at any point in time, if I have to check for the existence, I just need to search this element in that hash table. If it is found in the hash table, then I know that it occurred in the past. And that's when it occurred in the past, I pushed it in the hash table. This is the golden pattern. Basically, if there is anything that you want to take away from this set of lectures, it is this pattern for hash table. I will show you countless number of times questions wherein this is the pattern, and that's why we use hash tables. Yesterday also, the group anagrams question that we did had this pattern. You had to search for a group, and you have to search whether the group occurred previously or not. If it occurred previously, then you used to append the current element to that group. Otherwise, you had to create a new group. So the problem was the same. You had to search for the existence of a group there. Here you had to search for the existence of an element. So that's basically the golden pattern. So the approach is clear to everyone. Shall we code it? So coding is really, yeah. Let's code it. Okay. So you have, now let's see. Let's first do the part after the decimal. Okay, let's do step by step. If So first things first, we will find the sign. So my result is, I have a string as the result, which is empty. Okay. Now first, let me find the sign. So for the sign, I just need to check whether both of them are of opposite sign or not. How do I check if both of them are of opposite sign?
We multiply if it's less than 0, it's opposite, right?
Come again?
We multiply numerator and denominator. If it's less than 0, it's obviously the sign will be negative.
Yes, you can do that. So basically, this is just some so if both of them are, if the product that you multiply is less than 0, 0L is just long, so that it doesn't overflow. It might still overflow. If it overflows, then we will have to check individually if numerator is negative and denominator is positive, or if numerator is positive and denominator is negative. That we will have to see. But let's come back to that. So if it is negative, then I have just appended a negative. Okay. So now I will populate the number before the decimal. So that is basically numerator by denominator, right? So let's keep a temporary variable just to make things readable. You can choose not to keep it also. And you can simply check that you can simply put it. So just convert it to a string and append it. Right? Now you will populate the dot. This is the dot. And finally, you will populate the part after the decimal. So let's call that void populate post decimal. And you have a X, let's say you have a Y. You can call it a divider and divisor if you want for better naming. You have a result which you have to keep appending. So what is the populate the part after decimal? Here you will call it with populate post decimal, and your numerator will become yeah, let's so this is the remainder, right? Modulo. So you can, so your numerator is temp, you can pass temp into 10, right? And you can pass your Y will be denominator and your string is result. Just one case, if the remainder is 0, then you don't populate this, right? So you can take care of that here. So if your remainder becomes 0, then you don't have to populate a dot, right? So just take care of that. So if the remainder is non-zero, then only you append a dot, right? You don't write 6.0, you just write 6. So that is the case that I have taken.
So if remainder is not 0, if remainder is 0, we don't even need to do this part, right? Populate
Yeah,
decimal.
so this will return. This we will take care of that here, that it returns. Okay, without anything. If remainder is non-zero, then basically there is a non-zero decimal portion, whatever you want to call it. So let's after you populate it, you can return the result. That's the skeleton, and this is the crux, the actual function. So this is basically the first part is keep appending zeros till x becomes greater equals y, right? So as long as x is less than y, you can multiply it by 10 and you can basically keep appending zeros. That's the first part. Whenever you get this will be in a while loop. We will see. We will come to that. Don't worry. Yeah, this is the first part. Is there any mistake here so far?
So before doing this, we need to check whether x is 0 or not.
Whether
Because
x is 0 or not. Yes.
If remainder is 0, the loop will go on infinitely.
Yeah, let's take care of the terminating condition after this. First, let's just complete the skeleton. Then we will see where all we will terminate. Okay, so after this, basically what you do is now you will basically divide. So you will basically, you can keep temporary variables again. So you divide them, and so your remainder is x modulo y. Now this is the part that if this remainder that you are getting is something that you have already encountered, then basically, so this is the part that if non-recurring, then you are fine. Let's see the case of non-recurring. So what we will do is we will have a map here. I gave you the syntax yesterday. So this map will basically contain all the numbers that you have visited, right? So you can have integer map, and here you can find the remainder. So if that remainder is not found, that means it is non-recurring. So in that case, you are good, right? So what you can do is you can append the remainder to this. And for this next iteration, your x becomes remainder. So you can append the temp for this, the quotient, and the remainder basically becomes the next iteration start, right? Otherwise, if it is recurring, right? So if it is recurring, then what do you have to do? Now this is the point. So basically, if it is recurring, then you can put it in the map also that you encountered this remainder, so that you don't And if it is recurring, then basically what you need to do is you need to go back to this position and you need to put an open bracket and a close bracket. Correct? So how do you go back to the position?
So if we can iterate from the end, we need to go back to the remainder that we are seeing right now.
Yes. So how will
Can't
you
we do
see that remainder? Yeah.
Can't we do it using iterator ITE?
Iterator to what?
Iterating the reminders. We know the quotient, we know the remainder, so we can find, we know the dividend and we know the divisor. So can't we find the quotient?
But how will you know this index? So the question is, in this result, you have to find the starting index where you need to append this. Right?
Yes, sir.
So how can you do that? Can you keep it in the map itself? Can you do something like this? So what this does is, what have I done? For every remainder that I have encountered, I have basically, I am maintaining the position where the starting position in my resultant string where I put that number. Correct? This will make me do that, right? So now if I do m of rem, this basically gives me the returns the starting position of remainder, and that is basically where I have to append, right? Right? Everyone understands this? So then I can basically construct my string as, I can get the substring from 0 to m of rem minus 1. This gives me the first part. Then I can append this. Then I can get the substring from m of rem to the remaining, which is whatever is to the current. So that will be basically the total size of that will be. So substring, you have to pass the starting index and the size, right? The number of elements that you need for that substring from that index. So this will be m of rem. Do you know this substring API for strings? Others? Yeah, so you have to, can you just let me know? So you have to pass the starting index, starting position, and so substring basically on a string, it will give you the substring as the name suggests. Substring from the starting location that you specify here up to a certain length. So m of rem is the length, right? Because m of rem is pointing to the beginning where I am putting the remainder. So basically m of rem, so take an example if you want to understand that. So if m of rem is 2, what does that mean? That means that from index 2, you are putting in the remainder, right? So that basically means that 0 and 1 was your string from 0 to 1. So that length is again 2, right? So I'm just passing the length here and the starting index. So this gives me the first half of the string. just before the opening C bracket, then I put the C, which and then this gives me the remaining part. So the remaining part will start from which index in the in result? M of rem, right? That is the index from where I have to start, and I have to go on till the end of the string. So how many elements will be there in that? Res of size minus M of rem. And then I will close it. Do you understand this expression? You can ask me questions if you don't understand this expression. Others? Yeah, Akash, I can repeat. Let's finish it first. Then I'll come back to your question. Okay. So this will basically otherwise give me the string, and maybe I can break. Let's see. We will revisit the terminating conditions, all the terminating conditions. Now let's just revisit things. So generally, the first part is that you will enter here, and there is another terminating condition is that if so you get the first number that you want to divide here. So first things first, at entry, if you get negative, if you get the quotient as 0, you can simply return. Here you don't have to return. I just right. So if you get a quotient which is numerator which is 0, then basically you can just return. Then let's come to this part. So now we know that we have a non-zero quotient, non-zero x. So the first thing that I do is I keep I make it greater equals y, which is this part, right? Now after I make it greater equals y, I take the quotient and find the remainder. Okay, so now I will so let's say the first time it does not, this is empty, right? Map is empty to begin with. I'm just trying to do a sanity check, a dry run, to understand whether I have written the correct code and find out the terminating conditions. That's what I'm trying to do through this. So I will just check this map is empty to begin with. So what I am doing is I am pushing this remainder in the map, the starting location of this remainder, which is fine. The main point is that I have the quotient now, and now my for the next cycle my remainder becomes x again, right? And so after that, when I start again, if I get x is 0, then I can return from here as well. So this will then be enough. So now for the next cycle, if I get a remainder 0, then I know that it will return. So after at the beginning of every cycle, I know that if it is 0, then I will return. And then basically the next part is, so I keep having numbers till let's say I have some numbers which I keep putting, and then I come to eventually. So there are two ways this will terminate, right? Either it becomes 0, the remainder, in which case I will terminate at the beginning, or if it is recurring, then it will terminate, right? So this part I have taken care of. Let me just complete the recurring part. So in the recurring part, I am checking. So this remainder that I have encountered currently, I have already visited it. So I am just constructing the string and I am breaking. This looks good, right? Any cases that you can think which has not been handled here?
Sir, I have a doubt in while x less than y wala part. Sir, in this, like, for example, we have example 10 divided by 3. Like numerator is 10 and denominator is 3.
This will be remainder into 10 or remainder?
No, sir, I am talking about while x less than y wala part.
Bolo, bolo. Yeah.
But I think it will be y 10 into x less than y. Then we will append 0 only.
So I am passing it multiplied by 10.
Okay, okay.
And that's why I changed this here. That then for the next iteration, my x is rem into 10.
Yes, sir, yes.
Right? Do you understand this? So let's do some initial. You can return, it's fine. It is immaterial. Let's do some initial testing. So how will we test? Now this is also another exercise that let's do. Let's first test with divisors, perfect divisor. So let's do numerator as 15 and denominator as 5. Let's see. So this is fine. So for perfect divisors, it is running fine. So let's take care of this case, whether it is. So this is giving me a mistake. Why is it appending it twice? That's because I have not passed the absolute values. Yeah. That's the best. So then after this, basically you can just change your numerator. Wait, I will just change the numerator and denominator. So once you have appended it, you can just make everything as positive. Okay, so that will basically ensure that. So after this point, you have to just work with positive numbers. So that works. Let's do this. This is fine. Now let's take case of, let's take some finite decimal, terminating decimal, which is non-recurring. So let's take 16 and 5. This is also, let's see. So this part of my code is tested, I know, right? Now, so this part is now. So let's do. So 3 is fine, and then you get 1, 10. So you pass 10 here. So you straight away come here and you get a remainder of 0. And you have a quotient of 2. So 0 you have not encountered, then it should push it, right?
The temp should be converted to string while appending.
Oh, this is what you're saying, right? Yeah, this is the mistake. Thank you. Yeah. Let's see. So this is fine now, the terminating part. Let's do, now let's take the case when we have cycles. So let's say 10 by 3. So the problem is that it is putting a C bracket before the decimal. Now let's see why is that happening. So there is a mistake with this expression. Okay. So now let's try and identify this. So substring is, the syntax is what I said is correct, right? It is the starting address and the length, right? Or is it something else?
It should be m remainder -1, right? Because we are considering number of positions.
Where?
Line number 30.
This one or this one? Here we pass the
This
length.
one.
Yeah.
First one.
No,
Yeah.
here I just changed this -1. I removed this -1, which is now
Okay.
it should be fine. Because so this I wanted, so you can keep any notion. I am keeping m remainder as the value in this map is corresponding to the starting location where I am inserting that number. I am keeping that convention. So if I am keeping that convention, then here it will be res.size, not res.size -1, because till res.size I already have characters, and I am about to now append from res.size index. Right? So I am keeping that in the map and not -1. So that was the mistake. Let's do this and then we'll submit. So we are now testing this part of the code. So this is fine. Okay, now let's see. So 1/6, we have just missed a case here basically. So let's do it for this case. You have 1 which is coming in, then you have 4. So you will be passing it with 40, right? So 40 with 6, you will get a remainder of 4. But so the problem here is that when you get a remainder, if you have, so have you seen 4 yet? No, right? So then you append 6, and so there is a problem here also then. So you get a 10 and temp becomes 4, right? See if you want to just do this. I would have used the debugger of this. So I get a quotient of, so when I enter, I get a 40. I don't get a 40. I get a 10, right? So temp becomes 1 and remainder becomes 4. So now this remainder I have not encountered. So I put 1 here, which is fine. And then I recur for 40. So now.
But we haven't added 1 to the string, right?
We have added 1 here. 1 is fine. After that, we are missing the, so then again it starts all over with 40, right? So with 40 it starts. So now with 40 and 6 it starts. So with 40 and 6, now your temp becomes 6 and your remainder becomes 4. Right? And the problem is that you already found it in the previous case. But 4, did you append it? Do this as well if you really want. Yeah, 4 you did append it actually. So can you tell me the mistake? There is a very...
But actually, as soon as we find out the 4 is in the hash map, we are not appending the 6 again. We are directly going to the next step.
Which is fine, right? Because
we haven't appended 6 anytime. We have only seen the reminder once for the 1 and this time for the 6. The last time we have seen reminder is for different quotient.
Yeah.
So this quotient we have missed. From here it is repeating.
No, see, the point is, no, my question is, will this help? So remainder, once you have found a remainder, that means that you had processed that when you have processed that remainder in the past.
Yes, we have processed, but the last reminder we have got is because of 10. And the reminder we are getting is for different, right?
Yeah, so
maybe I think that's part we are missing.
yeah, so basically what we are doing, this should be, so what you have, so basically see, the point is, let's come back. So let's take example. Let's take 1 by 6 only, the question that we are doing. So in this 1 by 6, what's happening is you have 10 and 6 to begin with, correct? And you get a quotient of 4 and a remainder of 4, right? So you put this quotient here. 1 by 6 was the example. Yeah.
Quotient is 1.
Quotient is 1 and your remainder is 4. So now you put this quotient 1, which is fine.
Yes.
And now this remainder 4 you have seen. So let's say you mark it as visited, or you mark the index, the corresponding index, which is 2. Okay. So now the next time what is happening? The next time this 4 is basically the divisor for now. The next time you are doing a 4 by 6, correct? I mean 40 by 6 basically. So so you started with 10 by 6. Now you are doing 40 by 6. So now when you do 40 by 6, what will you get? You will get 6, 6 again, right?
6,4.
6,4, yeah. So you will put a 6, which is fine. What is left? Now you will do a 40 by 6 again.
But we don't put 6 over here, sir, because as soon as we realize that 4 is in the reminder list, we don't add 6 over here. We just skip this part and we will just add bracket to the 1.
Yeah, that's what we are doing. That we saw in the. But what is the reason for doing that?
Because actually the quotient is different. The numerator part is different. When the numerator part is 10 by 6, we'll get 1. As soon as we change to 40 by 6, only then it starts recursing, right?
Yes.
So
So
I
one.
said,
Mhm.
can in the hash map, can we add as value as a vector in which there will be two values, the position as well as the numerator part, I mean remainder part, not remainder part, quotient part.
So you can
Position as
just
well as
add the numerator. It's fine. That for
Yeah.
this numerator you encountered it.
Yes.
That will be enough. But with remainder also you can do it. So the pattern is repeating here. Here the remainder was 4. Here also the remainder is 4, but the pattern is repeating from here, right?
Yes.
So you can, I think you can do this basically. So will this be fine? So for the next, so what I'm doing is that I am basically finding that for the next iteration, what is my numerator? If I have already seen that numerator, then I am not doing anything. If I have not seen that numerator, then so this is like a look ahead that I'm doing. This will also fail some test cases. Let's try this case with this. Okay, let's move on. We will come back to this question, okay, towards the end of the class. But I guess you get the idea, okay, without stalling the class any further. Cool. Where are you guys? Are you guys slept? Did you sleep? Yeah, shall we move on? Okay. So then let's move on to the next question, basically. And we will come back to this question. Let's move on to this question. Try this question. This is a relatively easier question. I will tell you the number as well. So this is 554 lead code. So let's try this question. So what's going on in your head when you see this question? So the question is telling you that you have a wall and you are putting bricks here. So what you have to find, so you have bricks that you have put at various positions in the wall. What you have to do is you have to tell me the minimum, the position where, so what I have to do is I have to make a cut. So I will make a cut somewhere and I have to basically find a cut which passes through most number of these vertical lines, right? So I have to find a cut which breaks the least number of bricks. So it will break the least number of bricks when it is passing through the edges of most number of bricks. So in this case, maybe this will be the line because it only breaks one brick, and 2 bricks it does not break. So I have to find this. Now tell me, what is the brute force way of doing this? Can anyone tell me what is the brute force way of doing this? Hello?
So we can sum up each row, means cumulative sum we can do on adding them, and then we have to find the index for which there are same values.
Okay, what does that mean? I got you, like somewhat. So the brute force way of doing this is that for every index, every such index, you find out the number of bricks, the number of bricks which have their edges here, right? So you can just find out for every such vertical line that you are drawing, for every such position, you can find out the total number of bricks you are cutting or total number of bricks you that come on the edge, right? And then you can take the minimum across all these positions. That's what you have to do. Is everyone clear with this? At least that at a very high level, what you have to do is that for every position, you have to find out the total number of bricks that lie on the edge. And then you have to take the maximum across all these positions for the, so the result will be that position for which the total number of bricks that lie on the edge will be the most. Is this clear first? Yeah. So how do you do that in a brute force manner? For every edge, you fix an edge, and for every edge, you iterate through the entire array, right? And you can find out. So when you are in this row, you can find out whether you can keep a count. So how much time will that take? For every position, you are enumerating, going through the entire array. So the total number of, let's say this is n by n, just for simplicity. You can have n by m also. Let's say this is m and this is n. So for every n, what you are doing is you are going through n by m. So this brute force way of doing it is n into n into m. right? So how do you, so this is basically the brute force way of doing it. Now let's think about where can we optimize it. So what are we doing here? For every index, we are basically finding out the total number of bricks that pass through the edge, right? So this is one way of thinking. What are we doing is, for every index, I am finding out the total number of bricks on the edge. Now let's look at another observation here. Another observation that you can see is that for a particular brick, there is only one edge. So one brick is exactly at one edge, right? It is not at any other edge. So can you use this observation to optimize this?
Sir, can you explain what you wrote? A particular brick, there is only one edge.
So for any brick that you take in this wall, there is only one edge, right? In the sense that it terminates at one, it starts at one index and terminates at exactly one index, right? So basically, for this brick, where does it terminate? It terminates at this index. For this brick, where does it terminate? It terminates at this index, J, right? So that's what I mean. There is, for one brick, there is exactly one edge where it terminates. So basically what you are doing here, for every index, you are finding out, how many bricks terminate at this index, right? And then you are taking the maximum across all indices. Now I am saying that is fine. Now just look at this, that for one brick has exactly one terminating index. So can you think reverse? Instead of going after every index, can you go after every edge? So for every edge, can you enumerate all bricks that lie on that edge? All bricks that terminate at that edge. So think about this. If you are getting confused, just think about the fact that when you are having a wall, for every index, what were you doing? You were going through all the bricks to find out which bricks were terminating at this index, right? So a particular brick was being visited n times if there are n edges. If there are n indices, if this is n, then one brick was being visited n times. But why do you want to visit it n times? When you visit a brick, can you keep the terminating index of that brick? So the unwanted operation that you are doing is that when you are at this index, you are checking whether this brick terminates, whether this brick terminates, whether this brick terminates, whether this terminates. Now when you are checking for this index, now again you are checking whether this brick terminates or not, whether this brick terminates or not, whether this brick terminates or not, whether this terminates or not. But you know that this brick does not terminate here, this terminates here, right? So can you optimize that search?
Sir, so basically where the maximum number of bricks will be terminating, that will be the answer.
Yes, that will be the answer. Yeah. Value is number of edges for that position. Yes, something like that. You're right. Yeah, I mean, think about it. Why are we like spending so much time on this operation when we are trying to find for a given index? Why are we like visiting the same brick many number of times? When we visit a brick for the first time, we know where it is terminating, right? Can't we just store it somewhere so that we don't have to like bother about it again? That's basically the crux. So for a given position, basically you have to find out. So this is again a search problem. What is the search problem here? The searching is that for a given position, you have to find out the total number of bricks that terminate at this position. Yes, you will use that, Shravan, you're right. I think Jadhav also got that. So think about this. For a given index, I want to find out how many bricks end with that index. So can I keep some structure wherein I have that information? So basically, can I keep a map such that for every terminating index, for every terminating position, basically I have the total number of bricks that end in that position? Can I populate this? I can populate, right? I can keep going through each of the bricks and I know the terminating index of that brick. So I can increment the count for that particular terminating position in the hash table or in this container, right? So now I will have, for every terminating position, I will have the total number of bricks which terminate. Right? And then I can take the maximum out of all this. Does this make sense? Yeah, Radhika, you're right. Do I need to repeat this? So when you are at any given brick, what you are doing is you are basically incrementing the count for that corresponding terminating position for that brick. So from this structure, I am creating this structure to solve this problem. So this is a structure which I have been given in a very raw form. So I cannot search here, right? In this structure, if I, first of all, do you get the solution? Then we can abstract the idea. But do you get the solution? What will I do? I will keep, so I'll just tell you the solution. The solution is we will keep a map, and for every, we will visit all the bricks. Once we visit, encounter a brick, we know the terminating position of that brick. We will increment the counter in the corresponding terminating position in the map. And so now I will have this structure wherein I will have the number of bricks corresponding to every terminating position. I just need to find that terminating position which has the maximum number of bricks, and that will be my that will be the basically the line index where you have to draw the line. So now let's see the question. What is the question? Like, what did we do in this question? Basically, in this question, you had the input in a certain form which is not fit for searching. Here you have to search, right? What do you have to search? You have to search for a given index. You have to search, or for a given terminating position, you have to search how many bricks end at that terminating position. But with the given data structure, that's a 2D array, this searching is not efficient. Why? Because you will have to go through, for every index, you will have to go through all the bricks to examine which brick ends where. So I just converted that into another structure which makes my search easier. So here, what did I do? I converted this into this, that for every terminating position, I enumerated the total number of bricks which end at that terminating position. So now, and then with that, basically, I told that then basically the maximum out of this is basically the answer. Let's quickly see the code. I think it will become more clear once you see the code for it. So this is the total number of rows. The total number of columns. So let me go through all the rows, all the columns.
So columns will not be
Yeah,
same.
columns will be not the same. I know. That's what I will do now. It's okay. So now I have this. So now I've gone through. So how will I find the position? So the position is basically the sum, right? So this basically gives me the position. I have to take the cumulative sum. So the third brick terminates at 5, right? 2 plus 2 plus 1. The second brick terminates at 3, 1 plus 2. So that's basically what I have done here, that I am taking the position where it ends. And now I am just keeping a map. So for this position, I am incrementing the count, that I have encountered a brick which terminates at this position. And I can take the maximum here also, or I can take it afterwards also. It is the same. It really does not matter. So I can take.
So we shouldn't include
we'll
count the last brick of each row, right?
Yeah, I know. This will be -1. I would come to that. And then basically you can return n minus result, right? You have to find the total number of bricks which you cut. So that is n minus result. Okay, look at this code and ask me questions if you don't understand anything. and let me know when if we are good to move on.
Sir, explain that for loop again.
Come again. Your volume is very low, Yadav. Can you?
Sir, explain that two for loops again, like
Yeah.
what
So
you did.
yeah. So I have basically. Look at this picture basically. So I am going through each of the bricks. So that outer loop is basically the row and the inner loop is the column. So this is the first column, this is the second column, this is the third column. For the second row, this is the first column, this is the second column, right? So I am just iterating through all the bricks and finding their terminating position. That's basically what I've done here. So for the first row, for the third brick, what is the terminating index? It is 2 plus 2 plus 1, right? It terminates at position 5. So I have just kept a position which is the cumulative sum of the lengths of the brick. So whatever is the cumulative sum of the lengths of the brick is the terminating position, right? For that brick. And I am just incrementing the counter for that terminating position. And I am taking the maximum with the current, whatever I have encountered so far. This is basically just to return, like you have to return the total number of bricks that you are cutting in the process. So that will be the total number of rows minus the number of bricks which you are not cutting or for which you are passing through the edge. Is this clear, Yadav?
Yes, sir.
Others? Can I have acknowledgements if you got it?
Clear.
Shall we move on? Okay, let's quickly move on to, yeah, I want to introduce another concept, but before that, let's look at another question. Let's try this question. Copy list with random pointer. This is 138.
So actually, small doubt in the question.
Mm-hmm.
There will be only one random pointer, right, at most?
Yeah, every list has one random pointer.
Not more than one random pointer.
Every node, yeah. So what is the complexity of the previous question, by the way?
It would be n plus m. M is the maximum column length of a row.
It will be m into n, right? I mean, yeah. Maximum number of columns into m into n, right? I mean, if so, it will be basically the total number of bricks.
Yes, sir.
So what is the problem? What is the challenge in this question? The random pointer, right? If there was no random pointer, you would have done that easily, right? You would have simply gone through the list, and for every element of that list, what you would have done is you would have copied the next. The problem, the challenge in this question is that you have a list. So if you start copying this list one by one, the main problem is that for a given node, the random pointer of that node might be pointing to a node which you have not yet malloc. That's the first challenge. So what is the problem? So let's see the problem. Everyone, first of all, do you understand what is a deep copy of the list?
Sir, could you repeat that question now?
Yeah, I will just repeat the question. So the question tells you that you have a linked list with, so linked list, I guess everyone knows, right? Linked list, the only modification in the linked list is that apart from a next pointer, every node of that of the list has another pointer, which is the random pointer, which can point to potentially any other node in the list. It can point to null also. It is perfectly okay. You have to make a deep copy of this list. So by a deep copy, so basically see, copying the any location in the memory, there are two ways you can copy this. One is you basically have different references to the same location in the memory. So let's say you have a location in the memory X and you are referencing it through A or B. So then you have shallow copies of X at A and B and you are referencing them. Whereas a deep copy is an exact replica of that memory that you make at some other location of the memory and then you access it. So then it is called a deep copy. So for instance, if you have X here, a variable, and you want to make a deep copy of it, then let's say you created another variable Y at a different memory location, which has the same value as X. So then this is a deep copy of X. Why? Because now when you change here, it will not be reflected here. This is a shallow copy of X in the sense that you have exactly one copy in the memory and you are just referencing it at different places through different names. So A is a copy of X, B is also a copy of X, but these are all shallow copies of X. Here, if you have A, which is copying, which is actually referring to this location in the memory, and you create another copy B, wherein you replicated the location and the value, then this B is a deep copy of A. Do you understand deep copy and shallow copy now?
Does the changes, if we make changes in X, will it affect on Y then?
Where? Here it will not.
Okay.
Because you have replicated that. So think about it in terms of in terms of basically drive sharing, like one good example is drive sharing. Yes, Karan, location will be different. So in drive sharing, what do you do in Google Drive sharing? You have some document which you have uploaded to your Google Cloud server, right? And you share it with others. So when you share it with others, the others also refer to the same document. They have copies of that document, but they are referring to the same document. And so if you make any changes to this document, it is immediately others also get to know about it when they are referring. So this is basically what the drive is doing, is it is making a shallow copy of your document. So everyone has a copy of your document. Your friend also has a copy of your document. With everyone with whom you have shared this document, they have a copy. Each of them have a copy of this document. But it's a shallow copy because there is exactly one instance of that document, and that is actually in the server of your Google Drive. Others are just referencing to the same location. So that's a shallow copy. Compare that with a scenario wherein you, let's say you sent that document via email to everyone and you told them that, hey, upload your own copies in Drive. So now basically your Google Cloud server has a copy of the document. Their Google Cloud servers have another copy of the same document because they uploaded, let's say. So now this is for this document, this is a deep copy of that document that everyone is possessing. So any change that this person makes to this document will not be changed here, But for a shallow copy, any change that is made by any person will be reflected for all other persons also. So copying it, you are copying a document in both the cases, right? But this is a shallow copy. Similarly, the same applies to variables in the memory also. If you have a shallow copy of that variable, so copy is what? Copy is basically you want to reference the same value. So you have different functions, let's say F1 and F2, which want to use the same value, the same variable, right? You have a variable, a named memory location with some value. You have two functions which want to use the same variable. So what can you do? You will provide copies of this to both of them, right? That's what you will do. Now, when you are providing copies of this to both of them, the copy that you provide could be a deep copy or a shallow copy. So when you provide a shallow copy, what basically you are doing is you are giving them references to one centralized location in the memory. So they are still able to access this variable that they want. But any change that they make will be reflected in the others also, in the others copy also, because it's a shallow copy. The other way you could have given it to both the functions F1 and F2 is that you could have created two copies, two exact identical copies of the same variable and given one each to these functions. So then you have given deep copies of X to each of them. So now when F1 changes X or references whatever it does, it is not reflected to F2, right? So that is basically a deep copy. Copying anything is basically, why do you copy anything? Because you want it to be accessible to somebody else. That's why you create a copy of something. So you can create a copy of something either through this mechanism wherein you have one physical entity, exactly one physical entity, and you just give others a means to access the same physical entity. That's a shallow copy. The other way is you could replicate the same copy multiple times. So you have different physical entities. And now you give one copy each to each of them. So that's a deep copy. Do you understand deep copy and shallow copy? Both in the programming context as well as the abstract view as well, and the nomenclature. Does it make sense? Others? So here basically you have to make a deep copy of this list. So you have to create another exact replica of this list. You could have made a shallow copy of the list by creating just pointers to the same nodes and just returning the, so you could have done something like, if you had to do a shallow copy of this list, you could have simply created an array of pointers, and you could have made these pointers point to the corresponding nodes in the linked list, and you could have given this. So through this you can access the list. So it's a, or I mean, it's a shallow copy, but you want to replicate this one exactly. You want to create an exact replica of this list. That's basically the problem. So let's see, let's dissect the problem. What is the, so I know, first things first, I know how I can create a copy of a list without the random pointer, right? How would I do that? I can sequentially go through each of the nodes of the list and create a copy. So when I am here, I can create a copy for corresponding copy here, and I can make the previous nodes next point to this current node. So now when I'm here, I can create a replica of this, and I can make the previous of this point to this. And in this sequential manner, I can go about creating a copy, right? So this I know. Now the challenge here is that when I am creating a node, I know for sure I can populate the next pointer of that node, but I cannot populate the random pointer of that node, because that random pointer might be pointing to a node which you have not yet mallocked. And there is no way of going back, right? So that's the first challenge, that the node to which, so you are basically allocating a node and you want to populate all the pointers for that node, right? So you know that when you allocate this node, you know that the next of this node will point to this node. How will, so this node basically you will populate when you create a copy of this. So what do you do when you copy a list normally? Let's go through that process to understand the dissection of this problem. So what do? You will basically, let's say you have this photo now. Now, what do? You are here. You basically know that this nodes, the node that I am at present, the next of this node will be this node. So you can malloc a node similar to this node here, and you can make the next of the previous node, which is this node, point to this. And then what you can do is you can move the pointer here. Now you are here, and now you know that the next of my current node is basically the node that I am about to create. So what I can do is I can create the node that I am about to create, and I can make the next of the current node point to that node, and then I can move on. Now again, I know that the node that I am at currently, the next of that is basically the node that I am about to create. So I will create a node and I will make the next of this node point to this. So I can keep doing this and I will be able to create a copy of the linked list, right? Without the random pointer. This is how you do. So what do? You are at a current node. You basically populate the next pointer of the current node by and how do you populate the next pointer of the current node? You know that the next pointer of the current node is basically the corresponding node of the next pointer of the original list, right? So this is how you do it. Now the problem with this in this question is that for a given node, you can populate the next pointer because you know that that next pointer of this node is basically the next node, the corresponding node, but you cannot populate the random pointer of this node. Why? Because this random pointer might be pointing to some node which you have not yet mallocked. So you need two things. You need a way. So you need to ensure, first of all, that when you are populating the random pointer, that node to which you want the random pointer to point to, that node is created. So you need to ensure that this node just give me a second. I have a meeting which I will just start. 1 second. Yeah, so let's see. So you need to ensure that the random pointer of this node is the node that to which you want to point is actually malloc. So that's the first problem. The second problem is that when you are at this node, you know that for this node, the next pointer will be the equivalent node of this node, right? So you know that the next pointer of this node N2 will be the next pointer of, will be the node equivalent to the next pointer of N1. So the next pointer of N1 points to, let's say, M1. So now you know that N2's next will basically be the equivalent corresponding node of M1, which is M2, right? Similarly, when you want to populate the next pointer of the random pointer of N2, it will basically be the equivalent node of, just a second.
I think we have everyone.
So you will basically need to, so the random pointer of N1, let's say this points to K1. So the random pointer of N2 will be the equivalent node of K1, correct? Some node K2. So now, so you need a way of going from K1 to K2. So that's the next part. You need to have a mapping from old list to the new list. So these are the basic observations on this, on the basis of which this question is, or on which this question is hinged. I don't know how much of it made sense to you. Like it was a monologue from my side for 10 minutes or so. So is this first point clear to you? What I'm trying to say through this first point? Should I repeat it? So how do you get rid of the first problem? You can do it in two passes, right? if this first point is clear, how do you get rid of this first problem? You can do it in two passes. You can, in the first pass, just create the list, create an exact copy of the list without the random pointer. So that way you know that now the random pointer to which you need to pop the random pointer of a particular node to which you want it to point, you know that it is there in the memory somewhere. You have malloced it, right? So you can do the question in two passes to be able to get rid of this problem. Now this problem, do you understand this problem? You need a way of accessing the node in the new list from a node in the old list. So you can basically maintain a mapping from old node to the new node. So old node's address to the new node's address, so that when you are at a given node and you want to populate the random pointer of that node, what you will do is you will basically look up the random pointer of the corresponding node in the old list. You know the address of that. Use the map to reach to the corresponding node in the new list and make this random pointer point to that node. So in all, the total algorithm will look like, in the first pass, just create a copy of the old list without the random pointer. So create that. What does that mean? That means that you have an old list and you simply go through each of the nodes and you malloc a new node and make that the next node point to. So you just create a copy as you would do in a general case. That's the first part. And when you are doing that, store these mappings in a map. So store that this address is A1, let's say, and this is B1. Store that M of A1 is B1. M of A2 is B2. Do that. Then in the second pass, populate the random pointers. So how do you populate the random pointers? You can go through the nodes in the new list, get the random pointer from the old list, wherever it is pointing, go to the map, get the corresponding node from the new list and make the new list's node point to this. So that's basically the algorithm. Is this clear somewhat, the algo? I can repeat if it is not clear. Do you understand the two problems that I told you and the solution to that? Others? Can I have acknowledgements? I am not seeing a lot of activity from you guys. Yeah. So let's quickly code it then. So let's see. Let's do the first pass. Just create copy. So what do? I can, so current head or current old is, let's say, pointing to the head. I can have a current new, which will be the, and I can have a dummy. This dummy just helps avoid some cases. Just keep anything. Let my current new point to this dummy. Now what I do is as long as my current old is not null, what I will do is I will say that the next of the present node is basically a new node, which I will allocate, and the value of that will be current old's value. I can do this. So this gives me a copy without the random pointer. First, let me know, is this code clear? Are you guys familiar with this idea of using a dummy node? Like, how many of you are? Yeah, so this is just, you can get rid of this. So yeah, so what we are doing here is, see, this dummy node just takes care of the case that for the first time when you are inserting a node, when this current new is null, when this is null, then what do? You take care of that case separately, right? So then there what you do is you make, what do you do if you don't have a dummy? You will simply check that if this is the first node, which means if current new is null, then you would have done this. You would have done this, correct? Else may you would have done this. Correct? Without the dummy node, this would have been your code. Do you understand this first? Let's comment out the dummy. Without the dummy node, this is how you replicate a linked list, right? Any questions in this? Jadav, do you understand this? Bidyur, do you understand this? Divya, do you understand this? Yeah, now without the dummy, this was the, now what I do is I know that I need to just take care of the case when it is the first node of the new list. That is the case that I am taking care here. So I do a clever trick wherein what I do is I create a dummy node, which is not a part of the actual list, but I just create it and I make the new point to this, so that I always have a next to refer to. So then the first time I do current new arrow next, basically I am referring to the dummy nodes next. So my linked list now in this case is starts from dummy.next. So dummy.next is the linked list's head. Is this clear, or should I explain it on a whiteboard? I can explain it on the whiteboard if it is not clear. Jadav and Divya, because you guys are the ones who don't know about it. Think about it. What have I done here? So what have I done here? When I had this old node, old linked list, now I want to create a copy of this linked list, new list. So what I do, I have a pointer which is null to begin with, and I have a pointer which points to this node. So what I do is I take care of the case when it is null, then I just make this pointer get a new node, right? And after that, in the next steps, what I do is I make the current pointers next get a new node, and then I move this. So now, so this is what I do without a dummy node. So the trick is then what you do is you introduce a dummy node and you make this pointer point to this dummy node. So that now every time you will have the next node, the current node's next point to the new node that you are creating. Even for the case that when you are inserting for the first time. So because this was a dummy node, this is current new. So current new arrow next is not null. So you can then allocate a new node and then you can again move here and then repeat the process. And now my answer is this list. My answer is not this list. It is still this list. So my answer is dummy.next because dummy was a static node. That's why it is dot. So dummy.next is basically this, points to this node in the list, right? So my answer is this. Is it clear? Yeah, so that's just a trick that you use. If you want to avoid it, you can avoid it. It is not very significant. So I just copied it. And the next thing that I have to do is I need to create a mapping from old nodes to new nodes. So how do I do that? I can create an unordered map. But I have to create with addresses. So types will be node star. And every time I am doing this, so from old to new, right? I have to create. So this is the current old, and you know that the equivalent node is this node. So this is how I create it. And then in the second pass, what I do is I copy the random pointers. So how do I copy the random pointers? I make current new point to dummy again. I can make it point to dummy.next actually. Now I will just copy it. So current new arrow random will basically be current old's random is the node. I have to get the equivalent node of the new node. So the mapping will give me that and I can make it point. I can return dummy.next, which is the actual. That's because I am not updating this. So ask me questions if there are any in this code. Is the first pass clear to everyone? The first pass and the mapping? And the second pass? Others, is it clear? Yeah, so this
Sir,
Mhm.
you said that we are not pointing the first list through anything, right? Or does it? I didn't got correctly. Like dummy dot next, you said it points to the second one, right? Second node. Then if we have the pointer to first only, then where we will point that to? Do we have we taken that into case or anywhere?
I did not get your question.
You said dummy dot next points to the second node, right? In the on the whiteboard previously.
It points to the first node of the new list.
Okay.
Right?
Okay.
That's what I have done. I'm doing, right? It's just that the new list has one extra node before all the nodes, before all the actual nodes, which is the dummy node.
Okay, sir.
Others, any more questions on this? Clear? Shall we move on? So I just showed you, let me quickly summarize what we have done. I showed you 3 patterns so far. So I showed you a type of question wherein we had this idea that we need to look at and we need to check for the occurrence of an element from the past or search for an occurrence. So this was the question that we did. I'm just telling you the patterns where hash tables comes in handy. That's what I'm trying to do. So we looked at a couple of questions, group anagrams, and we looked at the first question of today's, which is fraction to decimal. Right? So in both the questions, the need was that we need to check for an occurrence of some quantity from the past. So in the past, if you encountered it, you need to find. If you have encountered it, then you have some other logic path. Otherwise, you have another code path. So that's the first type of questions we did. Then the next question that we did on the list, the pattern was that we saw that we looked at a case wherein there needs to be a mapping, explicit mapping from some entity E1 to E2. This we looked at in the copy list question, right? Here the pattern was that we needed a mapping from the old nodes as in the nodes from the original list to the nodes of the copied list, because that's the only way we would have been able to identify the corresponding node to which a random pointer of a current node points, and we would have been able to get to the corresponding node in the new list, right? So this is another pattern wherein hash tables or maps come in handy, wherein you have a mapping, explicit requirement of a mapping, and you can use the hashing to map. There is another pattern which also comes in very handy. That's basically with subarrays. If you want to find subarrays, so we will do questions on this now. These two patterns are clear to everyone? And do you understand it with the help of the questions that I took? Can I have acknowledgements if you understand this? Both of them, does it make sense at an intuitive level? Do you see the pattern in the question also, that yes, in the question you had this requirement? Fraction to decimal also you had this requirement, right? That if the remainder occurs again, then I have to tag this as a recurring decimal and close the bracket. If it is not, then it is still not recurring. In group anagrams, we had to find for the existence of a group. And then in the list, we saw that it was an explicit mapping that we needed to do. So what about the brick wall question? What was the pattern in that brick wall question? Can you abstract that?
Here also check for occurrence.
Okay, what was the occurrence?
The position of termination of bricks.
Okay, so you had to check whether the ending of the brick was, if that position has.
If it has occurred, then we are incrementing it, and if it has not, then we are inserting a new one with 1.
Yes. So that also comes here. Now, the third pattern of questions which warrant a hash map are questions on subarrays. And this becomes a little tricky. So let's illustrate that with an example. Try this question. $560.
So I got a basic idea how to solve the problem. I don't know whether it is right or wrong. So we'll maintain a sum array. I mean, we'll postfix array, suffix array, and at every position of the suffix array, we'll add it to the unordered map with the sum as well as the index of that array. So the sum we needed is to write. So when we are at position 3, when we are position 2, we have got what the sum we are required. So we'll increment a counter. And when we came to the position number 3, we need something number which is 1, so that the difference would become 2. So we will look for the positions where the suffix array sum is 1.
Yes, but you need to look at it in efficiently, otherwise it's n square.
Okay.
So to understand questions, so this is another type of question wherein you have to find subarrays with a specific property. Radhika, can you mute? I guess it's unmuted. I will mute you. Okay. They have muted. Okay. So look at this question. This question is basically you have to find subarrays that match a specific property. So everyone understands subarrays first? Right? Do you understand subarrays? Or should I explain you what subarrays are? Yeah, you understand subarrays, right? So I want to give you a view of subarrays which will help us solve these kind of questions, wherein you want to find the number of subarrays or find the longest subarray with a specific property. So subarrays are basically any array within the within the array with a specific start index and a specific end index, right? Any set of contiguous elements that you choose from this array forms a subarray, right? So one view of looking at this subarray is that this subarray is actually this entire subarray minus this subarray. Do you understand this? So I will tell you again. So this subarray is nothing but this entire subarray minus this subarray. And this view actually, so this is Sj, this entire thing is S, and this is Si. So Sj is basically nothing but S minus Si. And this view of the subarray is something that helps us a lot. So for instance, one very simple example is if you want to find the sum of this subarray. So this subarray sum is nothing but the prefix sum of this entire array minus the prefix sum of this array, right? And you could keep prefix sums as you are going iterating. So you can find the sum of this subarray in constant time, right? So this is the view of the subarray which helps us solve problems. So with this view, basically what we do is, if you generally enumerate a subarray, enumerate all subarrays, how much time does it take? What do? You fix one ending index of the subarray, and then what you do is you enumerate the starting index of all the subarrays. So basically you fix one I, and then you can go, start j with I and keep going here. And for every such j, it's basically you have a subarray which ends at I, right? Then you move your I. And then again for this I, what you do is you enumerate all subarrays ending at I by keeping a j and reducing j from I minus 1 to 0. So j for j I minus 1, you have this subarray. For j I minus 2, you have this subarray. For j I minus 3, you have this subarray, right? And then you move your I again, right? This is how you enumerate subarrays. And this total way of enumerating takes n square time. This part is clear? So in this kind of question, the benefit that you get by viewing this subarray as this minus this is that when you are at a given I, what that means is when you want to check for that property for all subarrays ending at I, that search becomes easier. So if you want to check whether this subarray satisfies this property, then what you do is you actually check whether this subarray minus this subarray satisfies this property or not. So this subarray you know, right? Because you are at a particular I. And for this subarray, whether it satisfies this property or not, you can actually store it. Let's take an example. Things will become clearer. So here, what you have to do is take this example only. You have to find all subarrays with a given sum k. Okay. So what I will do is my algorithm is simple. I will first find all subarrays ending at 0. Ending at 0 with some k. Then I will find all subarrays ending at 1 with some k. Find all subarrays ending at 2 with some k. This is what I will be doing. Okay. Now let's talk about how will I find for a given I, which means ending at let's say this is I, right? So for a given I, how will I find all subarrays with some k ending at I? So now for that, I know that if I take any subarray ji whose sum is k, then that basically means that the sum of this part is s minus k, where the s is this sum, right? So finding all subarrays that end with I with a sum k boils down to finding all prefix arrays with some s minus k which end at an index j less than I. Do you understand this? And can't you find all prefix arrays? So you basically came from here, right? So as and when you encountered a prefix array, you can store the sum. You can store how many prefix arrays you have encountered so far with a given sum s minus k in a map, right? So basically when you are at this index, you know that this particular sum is let's say h dash. So now you can say that m of h dash plus plus. So that basically means that I have encountered another prefix array with some h dash. So in this way, when you are at a given I, you have basically you have a hash table wherein you have prefix sums and the count of total prefix arrays with that prefix sum in that hash table. And then you can look up this sum s minus k in that map, and whatever count you get for that those are basically the total number of subarrays with some k, right? So for a given index ending at I, you can do it in order one time. And this you will do for all the indices. So this total will take order n time. समझ आया क्या ये किसी को? ये जो भी राम कहानी मैंने करी अभी. Others? So this is basically another pattern. Here also you are basically finding occurrence of something. So you are finding prefix array with a given sum, which you have encountered in the past. The pattern is the same, but this is a specific type of problem that you solve which has that pattern. The pattern is the same, that you have to find an occurrence of something in the past that has occurred in the past. Correct? So let's see the code for this then. So let's keep a map. What will I do? Let's go through all the elements. I can keep accumulating the sum. Right now, for this cumulative sum, what is the prefix sum that I want? Cumulative sum minus k. right? I want the count of so my total number, I will increment it by m of cumulative sum minus k, right? This will give me m of cumulative sum minus k will give me the total number of prefix arrays with some s minus k, and whatever all those prefix arrays will give me a sub array with some with some k. Correct? So this is what I will do. And when I'm here, I know I can increment for this prefix sum. This is the prefix sum. So I can increment that, and then result is the answer. There is only one case which is missing. So every subarray which I view in this manner, the starting I have not taken into account. So I'll just explain one thing. So in this view of the subarray, basically we are saying that every subarray is nothing. For this subarray is basically this entire subarray minus this subarray. So what is this subarray then? This subarray is basically this entire subarray minus nothing, right? So minus nothing you need to take into account, right? Otherwise, you are only enumerating all subarrays with at least one element with at least I equals j equals 0, right? So that part is what I will take care of here. So I will say that for that prefix array to be equal to the sum k, I will say that m of 0 is basically 1. So that basically means that sum 0, I have one array, which is basically the empty array. So that when I am at a given index I, if the sum from 0 to I is k itself, then that also needs to be counted, right? So what is the corresponding prefix array for that? That is the empty prefix array, which is what I have initialized here. We will just be storing the sum with the corresponding count. Ask me questions if you don't understand any part of this. Do you understand? Yeah.
Why m of 0 equal to 1?
So this is the empty prefix array. So see, when I am at a given j, I need to find for all the prefix arrays with sum to cumulative sum minus k. Right? So for the, what do you mean when you have an empty prefix array? That basically means that the subarray is the entire array.
Okay.
So I'm just taking care of the case when this entire, I'm at this I, right? When this entire sum is k itself, what is the corresponding prefix array for which you are doing s minus k? It is empty, right? So I'm just saying that there is one array, prefix array with sum 0. And that's what I have encoded in m of 0 equals 1 or assign 1. So that if this entire prefix array itself sums to k, then I will increment that also. Because for this, what is s minus k? S minus k is, s itself is k, right? So k minus k, which is 0.
Then why you are assigning 1?
1 is the count. There is one prefix array with sum 0, which is the empty prefix.
Okay.
Can I? I don't get it. So these are like, once you do it once with by showing, yeah, I can do a dry run. Let's do a dry run on some case. There is, it's not intuitive, Biju. That's why, that's the point of these classes. These are all from experience. It will be, it's very rare that you get a question and of this type and you are seeing it for the first time, you will be able to do it. It's very difficult. So it comes from practice. I have seen this pattern many times. That's why I'm able to tell it to you. But the first time I did it, I was not able to do it. So I just looked at the solution. And then multiple times then I did it, did the same pattern started coming again and again. Then you abstract that pattern, that, oh, this is the pattern. So there are these set of questions which have this pattern. Let's do a dry run. Things will become even more clearer. So you have an array. Give me some numbers. 2, 5, 7, 1. So we want sum 7. Let's take the sum k as 7. So this is the map. So for sum 0, I am keeping a count of 1 before I am beginning. So now I am starting. So cumulative sum becomes 2 now. So now when a cumulative sum is 2, I look for 2 minus 7. I look for minus 5 and I check, is there any prefix array with sum minus 5? There isn't any prefix array, so result still remains 0. Right? So I am here, result does not get affected. Now I move to here. Now when I'm here, cumulative sum is 7. So now I check, because this sum is 7, I check, is there a prefix array with sum 0, which is sum 7 minus 7, right? So I look that up in the map. There is one prefix array with sum 0, which is the empty prefix array. So in total meaning, what that means that this itself, the entire prefix array itself sums to k, right? So I increment my count by 1. And so when I was here, I did this, that for sum 2, I have one prefix array. For sum 7, now I have one prefix array, which is this sum. So now I move here. Now I have a sum of 14. So I check 14 minus 7. I check, is there any, how many prefix arrays are there with sum 14 minus 7? I look it up in the map. I see, oh, with prefix sum 7, I have 1. So I increment result. And what is the meaning of it or intuition? That this entire sum was 14 and this sum was 7, which is where when you post it. So this sum is 7. Right? Then you move on here. We have 15 now. You check for 8. Yeah, when you are here, you increment for 14 also. For 14, you have 1. Now, when you are here, you have 15. You check for 8. 15 minus 7, 8. Is there any prefix array with sum 8? No. So you keep result as 2 only. It's just that for 15 also, now you say that I have one prefix array with sum 15. Now I move here. I have 21. Right? So now I have 21 and I check 21 minus 7, which is 14. Is there a prefix array with sum 14? Yes, there is. So I will increment. What does that mean? What was the prefix array with sum 14? This array. Right? So I am talking about this sub array with sum k when I am ending here. So I increment the count, and for 21 also I put it in the table, and that's it. So my answer is 3 now. I have 3 sub arrays with sum 7. Does this make sense, Drishan? Vidyut, are you getting some intuition now? Yeah. So is it clear to everyone? Can I have acknowledgements if it is clear to everyone? The idea, the execution, as well as the, yeah, so this is one view. This will keep coming. I will show you many questions which keeps coming with this.
Sir, can you please explain it again?
Which part, Saurav?
Sir, actually my net got disconnected for a while, so I missed this part.
So you lost
Dry
the
run.
entire question, or you lost some aspect?
No, only this dry run portion part.
Oh, only the dry run. Huh? So yeah, dry run is fine. You can, so just do it basically. Um, you were here, right? You started with here. When you are here, you have just m of 0 equals 1. So you have one prefix array with some 0, which you have put in the map. Now you get a 2. So now you say that, now you find 2 minus 7. So you find, is there a prefix array with some minus 5? You look it up. There isn't any prefix array with some minus 5. So your result still remains 0. And you put, now you put this in the map. So you are saying that I have a prefix array of some 2. So I have just incremented the counter by 1. So now I move here. Now I know my total sum is 7. So now I look for 0. Is there a prefix array with some 0? Turns out there is 1, which is that the empty array. So this entire array itself is of some k. So I increment the result by 1. And now I put for 7 also, I put that I have encountered one prefix array with some 1, 7. So I just keep doing this till the end. Okay, just sort of do a dry run in your head also. You will get it. It's very simple. Like the idea is not simple. The intuition coming to the intuition straight away when you see the question is not simple. But once I give you the idea, it is fairly easy to understand that it works. Coming up with that same idea is difficult, but understanding that idea is not very tough. So here also we have the same pattern, right? That we are looking, when we are at a given index, we are looking for occurrences of prefix arrays. So we are looking for prefix arrays that occurred in the past with some k, with some s minus k, right? So you are looking for specific occurrences of elements. It's the same pattern that is coming in this question also. So this is basically the bottom line if you were to take from me. I'll try this question if you understand this prefix array theory. We will discuss this tomorrow. This is a good question actually. This is 974. Okay. Try this question. I will give you more questions which you can try on your own. But this question is similar, exactly the same idea. You have to find prefix arrays with a certain property, and that property is, you have to just deduce the property and just store the map with that property. There is one more question which you can do, which has the same pattern, which is contiguous subarray. Let me just pull out that question. This question. This is 525. So you can try this question also, 525. Both of them have the same prefix, the subarray pattern, the view of the subarray that I gave you. Okay, So try these questions. Yeah, so we will meet tomorrow again, and we will wrap up hash tables, a couple of more applications of the same pattern, and then we will start with binary search trees. I will take a question wherein we need ordering, and through that we will motivate the need for binary search trees. So yeah, the class officially is over now. Thank you for joining, and good night. Take care. I will see you guys. I will be debugging the question on fractions. If you want to stay around, you can stay around. I will just do it. So if you want to have a look, you can, and suggest things, you can stay around. So let's just debug that question and finish it off. But officially it is over. Like if you want to leave, you can leave. I'll just share the screen for the fraction to recurring decimal, and we will see where we what we did wrong. If you want to debug. So let's come back to the idea. Why did we, like, why were we so basically the idea was that let's see this idea again. So what are we saying? Let's say we are doing 11 by 6. So what is that? This is basically 1.8333, right? So it is 1.8333. So 1.83. This is it. 1.833333. So what is the pattern here? What is repeating basically? So you had a sequence of numbers after the decimal, obviously. Now, when you are here, if the number that you are about to put is the same as a number which you had put before, then it is recurring. Is that right? Like people who are there? I'm just yeah, Shravan. Hello. So this is basically what, if I have seen the number, then basically, so I can do it on the quotient also, right? Because I'm putting the quotient here. So if I have, can I put it on the quotient?
Sir, I think only with the quotient we can do that, because the quotient may repeat, but still there is a chance that it's not recurring.
Yeah, because the divisor is different.
With the combination of quotient and remainder, we can do that. I think that may work.
With the combination.
Yeah. So if we store the values of the numerator and we increment, we store the values of the numerator instead of the remainder.
That's what I was coming to. So numerator is just remainder into 10, right?
Yeah.
So we were storing that also. I mean, numerator is nothing but remainder into 10 for the next iteration, right?
So, but if we consider the case of 1 and 6, in that case, we were getting like 1.0.16. So in that case, we were multiplying. We were getting the storing the remainder. In both of the cases, we're storing 4. But in case if we store the numerator, in case, so we will store 10 and 40, and then will come 40. So which will be a valid set.
Yeah, it will be. So you have
mostly there will be certainly some cases in where storing numerator
10 is fine. So if you had, see, if storing numerator will work, then storing remainder will also work, because remainder is the numerator only for the next. Remainder into 10 is the numerator. So if If remainder occurs, then numerator also occurs. If remainder does not occur, then numerator also does not occur. Right? Will that be a big factor? I don't think so. So here the problem is that in 1/6, the problem is that we have encountered 1 as the remainder. Now we are encountering 4, and the next time we encounter, so after the decimal, in the first case, when I am dividing 10/6, I am having a remainder of 4. So basically for the next iteration,
so we will also get the remainder 4 if we consider the remainder.
yeah, we will get a remainder of 4. So I will put
like
1.
supposedly for this test case, if we consider the like numerator, like after like first we're storing 10, then we'll be storing 40. 40 will increment, I will give a count to 1. Then the next time when we'll store 40, then we'll find that, oh, this value is already updated, so we'll provide the else part. If we are doing the reminder part, then we are getting 4 in the first, and then like during 40 we are also getting the 4 as the reminder, because of which we are getting the bracket in the one part. Like considering this test case.
So for this test case, no, so for this test case, see, the part is that you have 1/6, and when you divided 10/6, you got a remainder of 4.
Yeah.
So you put 1, which is fine, right?
Yeah.
Because you have not encountered a remainder of 4. Now you have 40.
Yeah.
And with 40/6, you are again getting a remainder of 4. So basically what you are saying is that
So we are encountering the remainder again. Instead of storing 6, we are actually encountering the remainder. So because of which it goes to the else part other than storing it.
Yes. Right. So for that one, you had 4 remainder, which
yes, sir,
resulted in. So that's why Shravan is saying put have both quotient and the remainder.
So try putting only the quotient.
Only the quotient is not right.
Sorry, only the numerator. I did mean the quotient.
Numerator and remainder are the same, right? See, if you do it by just the numerator, here you have first time you will have. So when you first time you will have 10/6. So you will you put 10? You will not. You start. You get a quotient of 1 and a remainder of 4. So the numerator is 40 now for the next iteration. So will you store 40 here in this iteration, or will you go to the next iteration without storing?
We will store. We can the 40 will get stored, right?
So if you store the 40, then the next time you have 40. You
yes.
say that you have encountered 40 already. So the next time you will.
At that time we have already got 6. We have already inserted the quotient 40/6, which is already 6. So by that time we have already inserted the 6 part. So after that it will get only repeated.
Will you have inserted 6?
Yes, sir. Like during the first time when we have encountered 40, then we'll add the value string, value 6 to the string. Then we'll multiply it with multiply the remainder with 10, which will again get 40. So the next time when we go to a if else loop, then we'll find that the value of 40 was already updated. So we'll go to the else part.
So that then also 6 will not come, right? You will only get 0.1.
It will come, sir. I think so.
You can store both the quotient and the remainder. That makes sense. If you have the same quotient and the remainder, then it will be fine. But yeah, you can store the next numerator also. Let's try the next numerator, what Saurav is saying. I think that makes sense. So when I'm here for the first time, what I do is I have some numerator. So that numerator I know I have not encountered. So that's basically how I enter the while loop. When I enter the while loop, I know that the current numerator X I have not encountered before. So I will simply get the quotient and the remainder, and I will append for this quotient and the remainder. I will append it. Now I know that for the next half, this is the numerator or the remainder. It is equivalent. So I will check if it occurs or not. If it does not occur, then basically I can say that the next one I can visit, and this is fine. And the X for the next part, it becomes a remainder into 10. So what I'm saying is I have come here. I know the numerator now, whatever remainder I had a numerator, and that numerator has not yet been included. So I will include it first, which is what I will do here. And so see, there are two ways you could do this loop. Every time you could ensure that you always pass the numerator which is valid, so which is non-recurring. So in that case, the structure will be that the first half of the while loop will be for processing the numerator, getting the quotient and appending it to the string and marking it as visited. And the second half will be for checking whether the next possible numerator, and if that next possible numerator is recurring, then terminating. Right? That will be the skeleton of the high level outline of the code. So this is the first part. I am assuming that whenever I enter, or the other way you could do it is that you could assume that any numerator could enter the while loop. The first check that you will do is for whether the particular numerator is recurring or not. And if it is recurring, then you could break. Otherwise, you would do the processing and then continue with the next, right? So those are the two ways you would write this while loop. I think what I have messed up here is that I have mixed both of them. So what we have to do here is, so I have some numerator that I am passing. I haven't yet checked whether this numerator I have seen or not. Let's not bother about that. See, this and this thing, both of them are conflicting. So let's assume that when I enter, I know that it's a valid numerator that I will always enter in the while loop. So if it is a valid numerator, I will keep appending. 1 second. And once I keep appending, I will get the number that I need to put. and I will say that I mark it as visited, that I am about to insert it here, right? I mark it that I am about to insert, and then I insert it. So now I know that this numerator has been processed completely. Now I will look at the next numerator, which is basically the remainder. So now I will check if this is non-recurring. So now there are three things. If this remainder is 0, then I can return. Otherwise, if the remainder is non-zero, then is it recurring or not? If it exists, then I can, if it does not exist, then I will continue with the new numerator, which is rem into 10. If it exists, that means I cannot continue. So I will find the substring, which is this itself, and I will append closing and opening C, and I will return. So that is, I think this should be fine. Now here you will have to just take a check that if temp is not 0, then you call this, because I am assuming that as soon as I enter the while loop, or you could do it here only if x is 0. So because I'm assuming that when I'm entering the while loop, I have a valid numerator to divide. So I think this should be fine. Let's see. Let's see 1/6 only. Temp is the next numerator. Why didn't it enter if temp? So now I have entered. For this I have this remainder, which is 4, and then I will for the next iteration, my remainder is 4. So I mark that 4 as visited. This should. So once I come here, I have 10/6. So which is 1. So I put 1. And for this particular quotient, what was the remainder? It will be here.
So there you have updated the value of here the reminder will come 4. So m of 4 you have updated. Again here checking down that if m dot find rem. Like already we have updated the value of 4, and then we are getting that
it's still a bug. The bug is, see, the bug is here. I should not update for the new remainder. I should update for the remainder corresponding to this x. Right?
Yes, sir.
That's the bug. This should not be rem. This should be the previous remainder that I got.
So then why don't we first
so then let's do the other way, wherein let's when we enter, we check for the sanity.
Yes, sir.
And
If
then,
and
yeah, let's just check when we enter, and then towards the end, we do the processing. Okay, so now I can get any x. That's what I'm assuming. So if I get a 0, then I have to return. If I get an x which if I get an x which basically exists, then I can construct this and return. Let's just say this code is fine for now. We will come back if this code is not right. Otherwise, so now I know that this will be all x. So now I know when I'm here that this is unique. This has not been encountered before. So if this remainder has not been encountered before, let me just multiply it by 10. It does not matter. You can, and then you can keep appending zeros. And for the, so now when you are here, it's a valid x, right? So now because it's a valid x, you will do the processing. So just do the processing. This is all the processing that I have done. And when I do the, after I am done with the processing, I will append it. So when I'm doing the processing, I will just say that I have encountered it, which is here. I will put it. So now I know that I am processing it. So I have just marked it as visited, that I am processing it. Now I just process it and append it. Till here, it's fine. Now is the next iteration. For next iteration, I will prepare. So for next iteration, if I am preparing, x is just remainder. And all this is not required.
so then at the calling part, then we have to remove, we have to keep only temp.
Yeah, the calling part will keep only temp, and this is also not needed then. Because you will take care of that case. You are telling that anything can go, it's fine. You can. This works now. Let's do some more cases. Let's do 2 basics only. Okay, let's try to submit now. This is out of bound. These are basic, very bad corner cases. No points for that. This is basically end of, this is an integer which is end of. So basically this part is getting screwed. So as I was, this was my hunch. I was thinking that this will, so if numerator is negative and denominator is positive, or numerator is positive, you can do that. This will take care of the overflow. Yeah, the next issue then is keep all these as long. Yeah, this is bad. So just keep all these as long then. When you are multiplying, so just make everything as long. I would do what I would do is
I would second that. Completely unnecessary.
we cannot use the same name. I was just thinking, can I just typecast? Let's do num1. It's okay. This will just take care of that. This is fine. Now you can multiply actually, but now just you can do this.
Yeah, I would say that there is no benefit and there are definitely risks.
Say if num1 into den1 is negative,
okay,
just find replace numerator everywhere.
Yes, for the sync. So mostly the document talks about what we discussed. So we had discussed pretty much these things. So I think we need to reframe the requirement and maybe we will add what we
Now make all these long.
so that I mean it has the feedback also added into the same document. Cool.
This is fine. Position is fine. This you can actually still keep integer. I don't think that will cause a problem here. Let's see now.
Okay. Can we have a sync point on ditch in the Word document format? Yes. Okay.
We have it. So this works now. Let's just comment this out and submit. Okay. So what was the issue? The issue was just the convention. When you enter the loop, you just fix. See, generally, whenever you enter an infinite loop, the rule of thumb is you decide an order. Do you want to talk about the terminating cases first, and then assuming that this is a valid input and you don't want to terminate, process it, and then prepare for the next iteration. That is one format. The other format is that you could assume that when you enter the while loop, you have a valid input. So you will have to take care of the case here somewhere and then make sure that you enter as a valid input. And once you have entered as a valid input, what you could do is you will process it. Then you will get the next input and check whether it is valid or not. If it is not valid, then you terminate. Otherwise, you will continue. Right? Do you guys get the mistake and the idea? Like, anyone else who followed other than Saurav? I don't know. Yeah, you got the mistake, right? The mistake was, this is a very common programmer's mistake that we make. So always fix that first. The mistake that I did was I didn't fix it. I was like, okay, chalo dekh lenge kuch to. Once I start writing, I will figure out where to put what. But have that very clear in your mind when you're writing this kind of a code, which is what I did when I revisited it. Karan,
Sir,
does this make sense? Yeah, Saurav.
so like in case of like if we face this question in the actual coding rounds, there we can't see like in which test cases have failed. So how do we know that we have to convert the integer to long? So in this case, we have got a very bad test case. So
Yeah, generally those bad test cases are not there. They will have genuine test cases wherein overflow will not be an issue. It will mostly be like logic correctness. If your code is not correct, then it will. So they devise those test cases accordingly. That's why if you see this question has a lot of downvotes, 1600 downvotes and 740 upvotes, just because of the test case. The question is not bad. It's just that the test cases are like a pain. And so generally in the online rounds, you will not have these kinds of issues with the test cases with your code. If it is correct, if your code is correct, it will run. So in the test online round, if and when you get this, you will not need to probably do a long, or if you would do, then they would specify in the question that the constraints will be such that in the question you will be able to infer that things are going out of so here they haven't specified the range of numerator and denominator in the question, right?
yes, sir.
But generally in the constraints they will give you that. So generally it will be 10,000 or 10 to the power 5, which is well within the integer limits. But if the numerator or denominator goes 2 to the power 32 minus 1 or 2 to the power 64 minus 1, depending on your compiler, then it causes issues, right? So it will generally you get constraints in the question, so that constraints will dictate. But that's one thing. The constraints will that's a very generic answer that I gave, that for the constraints will dictate whether you will need to take care of overflow or not. But generally in online rounds they don't give, they don't test that ability. So they will give constraints which are well within the integer limit, but enough that it times out for n square. If they want an n log n solution, they will make sure that. So 10 to the power 7 is enough to test whether n square will time out or not, right? So 10 to the power 7 is well within input range. So that's how it will be. Karan, ये सही है क्या? मतलब समझ आया क्या आपको क्या किया यहाँ पर? हाँ, तो the issue was not really the remainder or the quotient. Remainder ही recurring है, मतलब that's okay. That's not a big thing. The issue was the coding convention. Yeah, so this is the code. I have done it with DSP batch login only, so you can check the codes when you at your comfort. So it's the same account. You can log in and check these codes. Okay. All right. If there is any other question, I can take it. Otherwise, I will end the meeting.
So you said in the doubt clearing sessions that you will solve the question, the rectangle question with the fewest number of tiles.
Yeah, that we will do. So we have a couple of lectures on backtracking. If you see the schedule, so there I plan to take some classical backtracking questions, and so as part of that we will cover the rectangular tile. We will cover n queens also. N queens is also a very classical question. And we will cover Sudoku also. Sudoku is also so in recursion, whatever we have done so far, it's just that I did not cover any classical popular question which generally has been asked in the past in the interview. So that's why I thought that I will have another couple of lectures wherein we discuss these classical famous problems like n queens, Sudoku solver. So we will do that, and as part of that we will discuss the rectangular tile also. That's not a very classical problem, that's a new problem, but that's still a good problem to illustrate certain ideas.
So I noticed in that very particular question we are getting two cases where we are getting a fixed result. Otherwise, excluding those two cases, in the case where m and n are 11 and 13 and the reverse, I'm not getting the values for that, except that all other test cases are passed.
Yeah, but if you properly do it brute force way, then it will pass all the test cases.
So like there, like if the values of m and n are generalized, then the brute force will not work, right? Like here the values are like constrained to like for 1 to 13, like the m and n values are up to 13.
Okay, but what is the brute force?
So like I didn't like go for the brute force.
Yeah,
Like we have
I
to
mean-
check for the areas, like we multiply the areas, and until and unless the area becomes 0, so like we will have to like minus the area every time, and we'll have to update the values of m and n accordingly.
Yeah, I mean, so whatever brute force I will discuss, that will, I guess, work for all NNM. It will not be necessarily restricted to 13, or it's just that with 13 we will be not getting a TLE because so.
Yes, sir.
Okay, I don't think the solution that I have in mind is really limited by the range of n or m, or it works only if n and m are less than 13. The correctness is still there for any n and m.
Okay, sir.
Yeah. Okay, any more questions? All right, guys, I will see you guys tomorrow then. Thank you. Good night. Take care. I will end the meeting.